nanohub.org.
Online simulation and more for nanotechnology.
Okay, so good morning, everyone. So I should explain, what this is all about. We're having two seminars this morning. I'm kind of the warm-up seminar. The main event is Dr. Shaloo Rakheja from MIT. We're talking about compact models, so SPICE models for circuit simulations, but we're talking about, the topic is how do you develop a physics-based model that can be used in circuit simulation studies to connect work at the materials and device level to circuits and applications. So it starts with a set of equations that you've probably developed that explain the physics of the device that you worked with maybe for a few years, and now you want to turn it into a model that works in a SPICE circuit simulation environment. And there are some issues that come up when you do that. And Shaloo has, deployed the very first model on our website. It's the most downloaded model there. It's been used by a lot of different people. And she's going to present a case study about how you take these basic equations that describe the physics of a transistor with this model and what issues arise when you want to develop that into a SPICE-compatible circuit model. So my task is to try to introduce those of you who aren't familiar with what this virtual source transistor model is to the model itself. We'll get the basic equations, then we'll take a break, and then I'll turn it over to the main event, which will be Shaloo talking about how you begin with those equations and end up with a SPICE model. So I'm going to dive into things here. This is the virtual source model. It was developed by Dimitri Antoniadis and his students and colleagues at MIT, and is continuing to be developed and deployed and used for a wide variety of transistors. Silicon 3.5, carbon nanotube, graphene, nanowire, maybe others. So it's proven to be a remarkably useful model. Very physical with only a few physical parameters, but it produces really good fits to experimental data. This is typical. We want to understand this model. Yeah. Now, I'm going to discuss it in a way that is not at all like the way that people who developed the model thought about things. It's completely different, but we'll end up with the same result. So this is kind of an experiment. I tried it out in my undergraduate class yesterday. It didn't go too badly. So, what I'm going to do is to develop the model using traditional approaches and concepts that you've probably seen as undergraduates. And then we'll see how, when we get down to part 4, with a simple reinterpretation of a couple of parameters in that model, we can make it work and it makes physical sense and accurately describes very small transistors. So this is how we do it. Here's our circuit diagram for the MOSFET. Here's what a typical IV characteristic looks like. It has these two main regions. There's this region at low drain voltage where it behaves like a gate voltage controlled resistor. So you just change the slope of the curve down here. This is the linear region or ohmic region. And then there's this region up here where it's trying to behave like a gate voltage controlled current source. So the current here is controlled by the gate voltage. The current is more or less independent of the drain voltage. Not quite. It's not an ideal current source. But we've got these two main regions, and then the curve smoothly connects one to the other. So let's start here. Let's understand, how you would do it in a traditional device course, how you would model this part of the region, and it's really very simple. Here's this cartoon sketch of the MOSFET, N-channel MOSFET, biased above threshold, so there's a strong inversion layer there. Simple MOS electrostatics says that the charge is negative because it's electrons, and it's just capacitance times voltage. But we're only interested in the part of the charge that's mobile, the electrons, and we only get that when the gate voltage is bigger than the threshold voltage. All right. Basic MOS electrostatics, 0 below that. So current is charge times velocity, and then there's the width. This is how wide the transistor is coming out of the page. Charge, we know, basic MOS electrostatics. Velocity, well, we just got a small voltage across the channel. We've got a constant electric field. the electrons move at a velocity of minus mobility times electric field. The electric field is just the drain voltage divided by the channel length, constant. We get this textbook expression. So, and this, still works very well. So this describes the linear region. Current is proportional to voltage, and the resistance of the channel depends on the gate voltage. Right? Really easy. Okay, so that part's easy to do. Then let's do the high voltage regime. So, and if we apply a high drain voltage, we have to stop and worry a little bit because we think, well, the electric field might get pretty high. And we know that in bulk silicon, the velocity is not proportional to the electric field. When the electric field gets high, we get increased scattering and you just can't make the electrons go any faster. The velocity saturates in silicon for electrons at about 10 to the 7th centimeters per second. If we look at a typical power supply voltage these days, it's about a volt. A typical channel length for state-of-the-art transistors is, roughly 20 nanometers. So that electric field is 500,000 volts per centimeter. That's a really strong electric field. We're way out here somewhere, right? You would think that the velocity should be saturated at Vsat. Okay, so let's assume that it is and derive the IV characteristics for high VDS. So current is charge times velocity. Charge is given by MOS electrostatics. It's even simpler now than it was before. We just assume that the field is high everywhere, the velocity is saturated, put these into the first equation, and we get this classic velocity saturation expression for the IV characteristic. All right, check. All right. Nice and easy. Okay, so that describes the high VDS regime of this device. Okay, so what we've done is we're trying to model this whole IV characteristic. We've done the linear part. That was really easy. We've done the saturation part, and it looks like, if we just take the smaller of these two currents, we have a 0th order model for the IV characteristic. So we'll just have to find out where those two curves intersect. We'll call that VDSat. If the drain voltage is less than VDSat, we take the linear expression. If it's greater than VDSat, we take the saturated expression. Okay, you just equate those two and we get an expression for VDSat. Saturation velocity times channel length divided by mobility. Okay, so this is the piecewise model we have. So as far as the inversion charge is concerned, we're assuming if we're above threshold, we have inversion charge. If we're below threshold, we don't. Now, subthreshold current is really important these days, so this is, we have to do something about this. And we have this model, either we're in the linear regime or we're in the saturated regime. All right. Okay. So if we could just make that velocity smoothly go from its value for low VDS to high VDS, we'd have a nice above threshold model, right? And something that we might be able to use. All right. That's not so hard to do. So you look at those equations and you say whichever velocity is smaller is the one that physically makes sense, If I were to just continue extrapolating mu times electric field, I would get unphysically high velocities. Well, if I write a little equation like that, the actual velocity is 1 over the linear region velocity plus 1 over the saturated velocity. Whichever one is smaller is going to be the one that matters. So when the drain voltage gets too high, the first term will become negligible and drop out. The velocity will be the saturated velocity. When the drain voltage is low, the first term will dominate, That'll do the right thing, right? Okay, so you put that two together, this would be the expression that we would get that would smoothly go from one to the other, right? That's not quite good enough. It does the right thing in the two limits. It doesn't quite get the shape right. Okay, but that's all right. So one of the things, you learn in doing compact modeling is that you have to have this combination of physics and empiricism. You don't want too much empiricism, or you don't have a physics-based model, but you really can't get by without a little bit at the right places. All right, so this is what we do. We just take that expression We multiply this by some power beta, and then we take this by a power 1 over beta, and now we've got an extra knob that determines the shape of the transition from linear to saturation. Turns out this seems to work remarkably well. You know, beta is typically in this range for a silicon MOSFET. If you're working at a particular class of devices, there's a particular beta that seems to work, and then it no longer becomes a parameter that you have to adjust every time. It basically describes these devices. You can even put some physics in. You know, if beta is 2, it sort of looks like a classic expression for the saturation velocity, or for the velocity versus electric field characteristic of silicon. So you can kind of motivate it where it comes from physically. Okay, so now we've got this saturation function that smoothly takes us from one region to another, and it's empirical, but it works pretty well. In fact, it works really well, and describes a transistor pretty good. So this is what I would call the level 0 virtual source model. You know, we're going to add a few parameters later. All right, the current expression, well, that's got to be right. This is a really simple description of MOS electrostatics. We have to do better than that to get any kind of reasonable model. The velocity in the current expression is this empirical saturation function times Vsat. That empirical function is given by this expression, and VDsat is given where those two curves intersect. So this works. It's not too bad. And then we can make it better. And there are only 5 parameters here that we have, you know, device parameters. There's oxide capacitance, so we know the thickness of the oxide. We know what that is. There's threshold voltage. You know, we can measure that. There's a saturation velocity. That's the physical parameter in silicon. There's the mobility in the channel, and there's the channel length. Right? So it's, you know, so it's kind of nice. With just a few parameters, you can do a pretty good job. Okay, so these are the 5 components, and now what I'm going to go through is step by step, just try to make this a little bit better and better, and we'll get something that's close. It's still not quite exactly the MIT version of the virtual source model, and I'll say a few words about that, but Shaloo maybe in her talk can tell me some of the things that they do that's special. So one of the glaring things that we're missing here, even though we're above threshold, is that these output characteristics have some slope. Right? You know, we've got to have that. And turns out, you know, this is something, if you read in the textbooks, you talk about channel length modulation, and this gets to be you know, the pinch off region and how it varies with drain voltage, and this gets to be a little bit complicated. So one of the things that I learned from Dimitri a long time ago is that if you have a well-designed transistor, something remarkably simple happens. You know, out here, the current is just charge times a constant velocity. The charge is Vg minus Vt. But there's this thing called dibble. You know, the higher the drain voltage, the lower the threshold voltage is, because it tries to pull the barrier down. It's like you have a gate voltage that's trying to turn it on. You have a drain voltage that's just as positive. It's pretty close. They're both trying to turn the device on. So the threshold voltage is its value at low drain voltage, and then it reduced by a dibble parameter, which tells us how sensitive it is to drain voltage. Now you measure this. Typically we measure this in subthreshold, where there's not much charge in the channel. We're way above threshold here, and there's a lot of charge in the channel. But in a well-designed transistor, if you just account for this, it works not only in subthreshold, it works above threshold, and you don't have to include any more parameters for channel length modulation and output conductance. Works nicely. Now, I'll point out, we're talking about, you know, when I think of this is a theory of a good transistor. You know, you can make bad transistors that are much more difficult to model, but if you've done everything right and it's behaving the way you want it to behave, in the end, it ends up being simple. All right, so now I have a level 0 prime model, and all I've done is to make the threshold voltage drain voltage dependent. Now we have 6 parameters because we've introduced the dibble parameter. Okay, so we're getting there. All right, so we've done above threshold. We should talk about subthreshold, you know, because this is really important. So how do we do this? So this is what the charge versus gate voltage might look like. So it's very small, and then around the threshold voltage it turns on, and if we're up here, charge is just Cox times Vg minus Vt. We were assuming it's 0 here, and we were modeling this with a straight line. But you would like to, first of all, you'd like to get this smooth transition. You know, maybe Shaloo will mention why you have to do that in a SPICE model. You know, you can't have these if statements. You know, if Vg is less than Vt, it's 0. If Vg is above Vt, it's linear. You know, those kind of things won't work in SPICE, so we have to make it smooth. But even more importantly, you know, this region is very important because that's the leakage current or the off current of a MOSFET. So we have to model that. And here I'm not going to, it's not hard to do. It takes a bunch of algebra, more than I want to go through, but we'll just get a sense as to how this all works. This is my band diagram normal to the channel. So it's P-type substrate. If we apply a positive gate voltage, we pull the bands down, right? You deplete the semiconductor, push all the holes away. But we're pulling the bands down at the surface, and the amount that we pull it down is called the surface potential. Now, this is a P-type semiconductor, so out here in the bulk, we have a few electrons, Ni squared over Na, right? Not very big. But the number that we have depends exponentially on the separation between the conduction band and the Fermi level. And since we're pulling the conduction band down near the surface, we're getting an exponential increase in the number of electrons near the surface. We're still not inverted here, right? There's still no inversion layer because we haven't pulled it down far enough. But we're getting more and more, we're getting an exponentially increasing number of electrons in there. Okay, so this is an expression that we can write down. If we want to know how much total charge do I have, if I integrate into the depths and I get all of the charge in coulombs per square centimeter, what would that be? All right, it's negative because there are electrons. There's a Q for the charge. This is the value in the bulk. This is how much it increases at the surface because we bent the bands down. And then I've got to multiply by the thickness of this layer, right? They're piled up near the interface, but they have some thickness. And you can estimate the thickness. You can just do it with dimensional analysis. It should be proportional to 1 over the electric field, because the stronger the electric field, the more you're pulling it to the surface. So it's proportional to 1 over the electric field at the surface. The electric field has units of volts per centimeter. So to get the right dimensions of this thickness, I have to have something upstairs that has units of volts. So KT over Q has units of volts, right? You put that in and just dimensionally it's got the right dimensions. Turns out it works really well. And you can derive it. It's just, you know, if you just integrate the electron density through that, this is what you get with a reasonable assumption. All right, so that's our expression. Now the difficulty is you apply a gate voltage. You know, this expression says that the charge increases exponentially with the band bending or the surface potential, right? But we only indirectly control that band bending with the gate voltage. So we have to relate that to the gate voltage. And there's an easy way to do that. You know, we think of the gate and the semiconductor as 2 capacitors in series. This is the oxide capacitor. This is the silicon capacitance. And there's a depletion region there. And, you know, we're depleted. We're doing subthreshold. There's no inversion layer. This is just epsilon divided by the width of the depletion region. So it's gate voltage. It's dependent on voltage, which is what the arrow is, but I'll just take some average value. Then I just have 2 capacitors in series. The voltage between those two, this is the surface of the silicon. So what I want to know is if I apply a gate voltage, how much is the surface potential? All right, so that's just, you know, beginning circuit analysis. That's voltage division with 2 capacitors. So the voltage here is this capacitor divided by the sum of the 2 capacitors. Okay? All right, and what we do then is we rewrite that. We rewrite this factor as 1 over m, and m is 1 plus the ratio of those 2 capacitors, and you can see that m is always a little bit bigger than 1. Unless you can find some way to make the capacitance negative, right? Which people are actually thinking a lot about. But this is what we get. So now we have a simple relation between the surface potential and the gate voltage. So we can relate this subthreshold charge to the gate voltage. Okay. And we'd still like to get rid of the electric field because that's something inside the device. You know, we want our expression to be in terms of things we know, like oxide capacitances and voltages that we apply, like gate voltages, not electric fields inside the channel somewhere. And that takes a little bit of algebra that I don't want to go through now. But, you know, Google ECE 612 Lundstrom, and you can find the lecture on subthreshold conduction, and it's not difficult at all. I'll just give you the final answer. Okay. So here's our charge versus gate voltage. This is above threshold. This is what the answer is below threshold. It goes exponentially with gate voltage VG minus VT divided by this numerical factor M, which is always bigger than 1. And there's a bunch of constants out front and oxide capacitances and things. So that's the textbook expression you'll find in any MOSFET textbook. Okay. Okay, so we have those two, and you know, we can describe this exponential behavior and we can describe this linear behavior. The difficulty is we don't have a continuous expression. We can do either subthreshold or above threshold, and that's not going to work in a SPICE model. So we've got this piecewise continuous expression. We know how to treat above threshold. We know how to treat subthreshold. And we'd like an expression that works in both. And there are a couple of ways you can do this. So you can solve this problem numerically. Solve the Poisson equation with the band bending numerically. It's not too difficult to do. I think people even do that in SPICE models. They call them surface potential models. Or we can do something empirical, like this saturation function, and see if we can find some empirical function that gives us the right answer in both limits and is accurate in between. That's what's done in the virtual source model. So the particular virtual source model, it was inspired by this paper. And what they did is they said, this equation should work, right? This is an empirical equation. It's not derived. But if you look at that equation, you can say that, well, if I look for low gate voltage, then it's e to some small x. So I have logarithm of 1 plus something small. Logarithm of 1 plus something small is x. So I just get the e to the q vg minus vt. I get an expression that looks like the subthreshold expression. Gives me the right result for gate voltages that are small. It's not quite right. Right? This was the answer we derived. This is the textbook answer that you get for subthreshold. You can see it's a little bit different. Instead of an m minus 1, we have an m, but it's pretty close. And you know, this doesn't make a whole lot of difference because, you know, you're worried about exponentially increasing with gate voltage. If you have a prefactor out front that's a little bit off, it's hard to see in any data or anything. So it's pretty good. Okay, what about above threshold? Okay, so then we can throw away the 1 there. We end up taking log of e to the q vg minus vt. That just gives us a vg minus vt. You know, above threshold, we get exactly the right answer. So that empirical expression will give us the right result in the limits, in the two limits, and actually gives us pretty good results in between. So this is our level 1 model now. So it's just like the last one, except we're going to use an empirical expression that treats both above threshold and subthreshold and goes smoothly between the two. We have now introduced one more parameter in the model. So this ratio of capacitors that gives me the subthreshold slope. But I still only have 7. Yes?
Did we not have beta as one of the parameters there?
Well, I'm not including it. Yeah, so there's a question about which ones, and I'm thinking you don't, yeah. Beta usually works for a class of device. Technically we should include it. And there's another one that we should include too. There are a few other parameters, and I'm trying to focus on the main ones that you adjust, and that have physical significance. Yeah. But beta is one that is there that you have to tweak. Actually, there's another one, alpha, and there may be one or two others. So there are a few other details in here, and maybe Shaloo will bring them up when it's appropriate. This is the actual expression used in the MIT virtual source model. It's like the one I showed you, but it's a little bit different because it provides a little bit better fit. And this is some of the things, what people do when they try to develop a model. So it's got an extra term there. We know how to treat VT. We have to include Dibble. But it's got an extra term there that I'm not going to say anything about. I don't know whether Shaloo will or not, but it's intended, actually, the threshold voltage changes between below threshold and above threshold. Now, below threshold, I said the charge goes as e to the q Vg minus Vt. Above threshold, I said the charge goes as Vg minus Vt. They're actually different Vts. Because one of the things that we tell students in beginning semiconductor courses is you bend the bands by 2 psi b, 2 times this psi b parameter that measures the difference between the intrinsic level and the Fermi level, and then you can't bend the bands anymore when you invert them. Turns out you can bend the bands a little more. And when you're on, you have bent the bands by maybe 6 kT more. And you have to account for this fact that in subthreshold and in above threshold you have different VTs. You get better fits. So this is a parameter alpha, and I'm, maybe both alpha and beta should be included as the parameters in this model, but you don't spend a lot of time having to adjust these parameters once you're working on a certain class of devices. At least that's my understanding. Okay, and we have to put series resistances in, right? Everything that I've discussed is I've assumed voltage is applied directly to the terminals of the device. But, your actual terminals are out here somewhere. There's some series resistance associated with it. So, there's little or no current through the gate. So the voltage you apply to the gate terminal is the voltage that gets into the intrinsic device. By prime now, I mean the actual, VD prime is the actual voltage that gets into the device. So it's the voltage on the terminal minus what you lose in the resistive drops. The source voltage is a little different. So, it's critical to account for those two. So we have to add series resistances in here. So now we have 8 parameters, or maybe 10 if we include alpha and beta. But we still have a relatively small number. So I've added a prime to all of these voltages, just to deduce these voltages refer to the intrinsic device. Then you have to add the series resistance and make sure that you account for the terminal voltages correctly. Okay, so we've got 8 or 10 parameters in the model. And this, I think, that's pretty much it. 8 or 10 parameters. Now, how many does an industry standard MOSFET model have? You probably know. It's 200 or 300, And of course, when you want to fit everything, you do need more parameters. But over years, I saw a book once where it plotted the number of parameters in a SPICE model versus time, and it just goes up as a straight line. Because, so what's nice about the virtual source model is it does really well with a relatively small number of parameters. And that's why people who come at it from a physics background like it. Okay, so now we want to talk about how you actually use this. Everything that I've discussed is standard textbook MOSFET theory, the way we've been teaching it for 30 years, right? How can you apply this model to very small devices? So we have to talk about this a little bit. This is, there are 2 things in the MOSFET current. This current expression, it's charge times velocity. The charge is MOS electrostatics. That's just the Poisson equation, right? It can get a little bit complicated. You have to worry about 2D electrostatics. People are going to FinFETs to properly control the electrostatics. But it hasn't changed in a long, long time. We understand the Poisson equation. The second part is transport. So this is what, this gets interesting. As you get smaller and smaller, you get ballistic or quasi-ballistic transport and all kinds, quantum transport, all kinds of interesting things can happen. So this is what you worry about mainly in a small device is we've used these drift diffusion expressions. How good are they when you get to these small devices? How can we expect to use those expressions in really small transistors? So look at mobility. The way you think about mobility, I've got a slab of semiconductor. I've got electrons that go through. They bounce around and scatter off of things. They're bouncing around at the thermal velocity, but there's some small drift velocity, and electrons drift in a direction opposite to the electric field, and the constant of proportionality is the mobility. So, this is the way we think about mobility, and it's a concept that if the channel is long or the resistor is long, then you can define a physically meaningful mobility. And people would say that this has to be many mean-free paths long in order for you to even talk about a mobility. Mobility was one of those 8 or 10 parameters in the model. How can we have a mobility in a model for a nanotransistor? So what's a typical mobility these days might be roughly 10 nanometers in a silicon MOSFET, I guess. A typical channel length, state of the art is 20 nanometers. 20 nanometers is not many mean-free paths long. So, using a mobility seems like it's not something that we should do. So, so let me talk about this for just a minute. A little bit of transport theory. If you take a transport course, one of the things you learn, we can relate diffusion is random thermal motion. So the electrons go around randomly, they scatter and they bounce around and go around in random directions. So VT is the thermal velocity, about 10 to the 7th centimeters per second in silicon. Lambda is the mean-free path. You look at the dimensions of that. VT times lambda has the dimensions of centimeters squared per second. That's diffusion coefficient. It turns out you have to divide by 2 to get the diffusion coefficient. So that's an expression that relates the diffusion coefficient to the mean-free path. The Einstein relation relates the diffusion coefficient to the mobility. So if I want to know what the mobility is, I can easily relate the mobility to the mean-free path. Longer the mean-free path, the higher the mobility. Okay. Usually we write mobility as Q tau over M. This is the same thing, just written in terms of mean-free path. That's all. And we would expect that in order to talk about a mobility, our channel length has to be much longer than this mean-free path, which it was in 30 years ago when the textbook theory was sound. Okay, so that's one issue that we have to deal with. How can we use a mobility in a model like this? So the other one that we should look at is this saturation. So this is a well-established physical effect, right? Shockley knew all about this. Velocity saturation in bulk silicon is something people have understood for a long time. The electrons gain a lot of energy in this high electric field. They scatter a lot, and you just can't push them, make them go any faster. These are Monte Carlo simulations from the IBM group a number of years ago. This is a simulation of a 30 nanometer channel length MOSFET. I can still remember reading this paper for the first time, thinking, this is like people would call it an academic exercise. Nobody's ever going to build a MOSFET with a 30 nanometer channel length. Okay, but we are now, or less. So this is the conduction band, high drain bias. Every dot here is an electron that's being tracked as it goes from source to the drain, gets accelerated by the electric field, scatters off of whatever things there are there for it to scatter off of, and this is a snapshot in time. So you can see the electrons flowing out of the source, they're flowing across the drain. They have a lot of kinetic energy because they're way above the bottom of the conduction band. And then when they get in the drain, they scatter and they lose all of that energy. So transport is actually really complicated. This high electric fields that vary rapidly, even, setting aside quantum transport, this is a very complicated transport problem for people to treat. This is the region, the slope of the conduction band diagram gives you the electric field. So our conventional understanding of velocity saturation is it occurs in high electric fields. So you would expect it to occur first here, and then as the fields get higher and higher, for more and more of the channel to be velocity saturated. Okay. This is what the average velocity versus position looks like. You just go at every position, you just add up the velocities of all the electrons and compute their average. This is what the velocity versus electric field profile looks like. Where the field is highest, the velocity is the highest. 10 to the 7th centimeters per second is there. Velocity does not saturate at 10 to the 7th centimeters per second. The reason it doesn't in these short devices is that they just zip across the channel before they have a chance to scatter very much. You know, in a bulk semiconductor, they can gain energy, they can scatter the velocity. There are these transients where the velocity will go very big, but then it will settle down in a bulk semiconductor. There isn't enough time or enough distance in a short device for all of that to happen. So this is called velocity overshoot. All right. So, okay. Now, so this is a mystery. You know, this model that we derived, you know, ignored all of this physics that we know is going on in these small devices. And yet we find that if we take this model and we fit it to measured data, we just have to take the mobility and we just have to tweak it a relatively small amount. So we'll call it an apparent mobility. And we take this velocity saturation, which we VSAT, which we know makes no sense at the nanoscale. And we just call it, we give it another name. We call it the injection velocity. And it's not that different from the saturated velocity. And you make these two, you could think of these as fudge factors, but they're only two parameters that you're tweaking a little bit. And then you can describe small transistors remarkably well. So there must be more to it than just empirical curve fitting. You know, there must be some reason that this works so well. So if you want to see the right way of doing it, you know, Dimitri and I wrote a paper, came out about a year ago, where we do this using the Landauer approach, and you can see where all of the results come from. I'm going to get the same answers, but I'm going to do it in a very simple way. And, you know, it'll look like I'm waving my hands a little bit, and I probably am, but I'll get the right answers, and I think it makes physical sense. And if you really want to see how it should be done to get it properly, you can read that paper. Okay, so here's the way you might think about this. When we think about a small device, this channel might be very short. An electron might go all the way from the source to the drain and not scatter. It might be shorter than a mean free path. Or it might be only a couple of mean free paths long, so we don't have a lot of scattering. The source and the drain we think of as very heavily doped large regions where there's a lot of scattering. So the electrons are scattering frequently in the source and the drain. They get injected into the channel. They might zip all the way across. As soon as they get into the drain, they scatter immediately again. Okay. So the channel is ballistic, but we think of these ideal contacts as always having a lot of scattering and being near equilibrium. So what this says is that an electron can never go longer than the channel length before scattering. In the bulk, it might be able to go much longer because there's no source and drain. But in a MOSFET, it can only go a distance L before it scatters, right? Because then it enters the drain. So I should again do the same thing. It's the smaller of the channel length or the mean free path in the bulk that matters. I can just write a little equation saying 1 over apparent mean free path is 1 over the mean free path in the bulk plus 1 over the channel length. Whichever one is smaller will be the one that will be the important one. Okay. And since mobility is proportional to mean free path, I could define an apparent mobility. I could just put that apparent mean free path in here, and I would get an apparent mobility. And my apparent mobility would look like this. This would look like something you've seen in your semiconductor physics. This would look like Mathiassen's rule. And we would say that 1 over the apparent mobility is 1 over the actual mobility in the bulk plus 1 over something that people call the ballistic mobility. And, you know, this is the actual mobility. It's got a mean free path there. The ballistic mobility has a channel length because the electron can't go any further from the source to the drain. It's going to scatter. And you can see that what's going to happen now is whichever one of these is smaller is going to be the one that matters. The ballistic mobility depends on the length of the channel. In a long channel device, this will be very big. And your apparent mobility will be your actual mobility that you measure in the bulk. In a short channel device, this will be very short. You know, and this one, so this will be a very low mobility. This term will dominate, and you'll get something that people call the ballistic mobility. You'll go between those two limits. So this is the physical definition of this apparent mobility that you have to use in order to fit measured IV data. So we just take our textbook expression, we replace the actual mobility by this apparent mobility. If you go all the way to the limit where your channel length is very short and you get to the ballistic mobility, then if you put this ballistic mobility in there for the apparent mobility, you get an expression for the ballistic current of a MOSFET. It's independent of channel length now, because electrons in the ballistic limit, they go across the channel without scattering. It doesn't matter how long the channel is, the resistance doesn't change. Okay, so we can make physical sense to one of those two parameters. The other parameter is the injection velocity. So the way we can think about this is we're focusing on the beginning of the channel, the top of this potential barrier that separates the source from the channel. This is what's called the virtual source. This is why it's called the virtual source model. The goal of MOS electrostatics is to make the charge at that point what it should be in an ideal long channel MOSFET. And, if you've done your electrostatic engineering well enough, that works. So all we need to figure out is what is the velocity. And if we look at this regime, we've got electrons coming in from the source at some velocity. So they're just thermal equilibrium electrons. And they come into that region. The electrons have to this is a region near the source, the electric field is low, right? It's high in the drain. So in order for the electrons to get across that region, they basically have to diffuse across that little region. Once they get across, they can go out at a velocity that can be very big, because there's a strong electric field that sweeps them out. So I've got three velocities, and again, you would think that the velocity at this point is going to be the lower of those three. Right? If this one gets low, everything is going to get backed up and it's going to slow down the velocity. So I can write an equation. 1 over the velocity is 1 over this velocity plus 1 over this velocity plus 1 over this velocity. And whichever one is lower is the one that's going to matter. Okay. This one is probably never going to matter, because you saw in those Monte Carlo simulations, we get velocity overshoot. In these strong electric fields, the velocities get very high. And this was interesting. 20 or 30 years ago, everyone was writing papers on velocity overshoot because they thought this velocity was the main thing to understand small MOSFETs. Turns out this velocity is the least important thing to understand, because once it gets big, it drops out. We only have to worry about these two velocities, right? Those two velocities determine the velocity at the virtual source. We know the charge at the virtual source. We know the current. Okay, so the V1 is the velocity that they come in from the thermal equilibrium source. That's 1 over the thermal velocity. V2 is the velocity that they diffuse across this thin low field region at the top. The diffusion velocity is just diffusion coefficient divided by the thickness of that region, how long that region is. Well, that's just the diffusion velocity. And again, if this region gets really, really short, the highest this velocity can ever get is the thermal velocity. If this region gets longer, your velocity will be less than the diffusion velocity. Okay, so this was our classic textbook model. We had a VSAT in there, which didn't make any sense. We just replaced VSAT by this thing we call the injection velocity. The injection velocity has a nice physical interpretation. If we say, well, what happens if my mobility is very high, which gives me a very high diffusion coefficient, or if the length of this short region near the source is very short, then this drops out and I'm at the ballistic limit, and that would be the IV. That would be the high drain voltage current of a ballistic MOSFET. Right. Current day silicon transistors are 60 or 70% of this limit. 3,5 transistors are even closer. They're almost at the ballistic limit. Right. Okay, so, we're almost done. So this is the model we had before. We just make a couple of minor changes. Instead of the actual mobility, we have the apparent mobility. Instead of the saturation velocity, we have the injection velocity. We've just attached physical significance to these two terms that were there to begin with. Okay, so So that kind of explains, now, as I said, this is not the route that the people who developed this model went through. This is not the way they thought about the problem. You know, I'm presenting it to a group of, you know, thinking that if you come at it with a background that you understand traditional textbook MOS theory, this is a way that we can understand how you get to the result that they got to. And you just replace the actual mobility by an apparent mobility, which has a clear physical interpretation. You replace the saturation velocity by an injection velocity, and it works remarkably well. Okay, so that's it. I'll just leave with 3 conclusions, and we'll see how much time we have for questions here. So, point 1 is the traditional textbook MOSFET models correctly describe the shape of the transistor, you know, and that's because, you know, this particular shape, you draw an energy band diagram. The way it works is you push this potential barrier between the source and the channel up and down with the gate voltage, and traditional models describe that. Okay, so they get that correct. But if you want to get the magnitude of the current right, they don't, because they don't treat transport correctly. But we can very easily take those models and we just replace the 2 parameters by physically relevant parameters, and now we can describe small transistors. And they're really not empirical, they're not fudge factors. They make physical sense. It works pretty well. Okay, so now that's a way you can understand this virtual source model. And now just to back up 1 or 2 slides, what Shaloo is going to do in the next talk, I think, is more or less begin. Assume you understand what this model is all about. Maybe she'll correct some of my view of what this model is all about. That's fine too. And she's going to talk about how do you take these equations and how do you turn them into something that can work in a circuit simulation environment. And it's not, you know, there are a few issues that come up that you have to think about. So we've done the physics part of it. Okay.